to have a little bit of understanding of some of the things you might have done when you did set theory, and just to bring back to mind what these Venn diagrams mean to us. Venn diagrams will serve like a useful purpose, even in the warm-up, like we did there. So remember, a Venn diagram, we'd like to have the universal set on here. It's like this whole rectangle is actually not just cosmetic, it's like part of the diagram. So I've highlighted, and each piece is like an area. The whole area would be, the whole thing would be 1, because it's like represents 100% of the outcomes, and then we might shade one of the events and its probability. So in yellow we have like the probability of event A happening, and it's represented by some area as a proportion of the whole, which is 1. So, and over here, this is, you might write not A. There's 1,000 ways to write not A, but A prime is a good way to write it, or if you have another way that you know is fine too. And you might shade it that way, right? That's not A. I'm just giving you 4 examples, but there are lots and lots of interesting ones you could do. You know, like can you show me the probability of like not A or B, or like what? Do a couple different things. There's A union B. I don't think we've talked about that symbol yet, but there it is. It's like the MasterCard area. There's the football area, right? That's A intersect B, which is the thing we were just talking about on the last slide, right? A and B occurring. That's the thing shaded. Okay, so you can picture these, and you can picture more exotic things with these Venn diagrams too. Like I said, like. Can you give a name for this crescent region, for example? Like if you were trying to shade that, like how would you write that down? Those are big questions. So I think you've thought about those things before. I just wanted to activate them in your mind. It's also important, I think, that we look at a Venn diagram. You haven't probably seen one of these very often, but I just thought I'd show it to you. Thank you. I'm here all week. Okay. Oh wait, I found another one too. No. I just pulled a couple.
I don't even own a cat.
I don't either. But I just pulled a couple, but if you want more of these, graphjam.com. You can find as many of these as you like. Okay, back to your regularly scheduled class here.
Wait, that's the
wrong one.
Yeah, that's the wrong one.
Do you want to, I don't know, let's do this. Why don't we do this?
Before the warm-up?
You want to go back to the warm-up?
Yes.
Let's go back to the warm-up. All right.
Yes.
It should be true that, like, together, the probability of IB is 0.02 plus 0.08, and is that right? Does it work out? And then likewise, okay, over here. And then just by process of elimination, she must have gotten that. Good job. Okay, so that's great. That's how I would like to see a Venn diagram. And then other questions that we can ask become very, very easy once we have this picture, I think, too. All right, and then part B and C, we didn't get a chance to talk about, but we will talk about them in a minute more formally. But like, I think it's actually not a bad idea to just talk about them just like shooting from the hip. Just like, how does this feel? What does this mean? Even if you haven't like thought about the actual formal algebra that might be involved in doing this computation, you can definitely understand what this question means as like a human, right? It means that like we're restricting our attention in this part B to only those people who are at IB. So can you imagine, you're like, tunnel vision, right? This is your world now, right? This is your world right here. That's all there is. It's right here. It's all there is. That's your world, and up in that world, what's the probability that if you're in that world that you have a pencil pouch? And the answer is, well, it's this region, the area of this region, divided by the area of this region. It's like, you know, geometric probability from, you know, back in the day. It's like a area divided by area thing, right? Football divided by volleyball, you might say, right? Okay. Okay, is that clear? Or over here, we're thinking, what's the total area of this? Divide by again. Take the football and divide by the volleyball again. You know, take the little area, divide by the big area, and this is your world now, right? If you're in this situation. Okay, and then we'll talk about D in a minute. But yeah, Jeremy, go ahead.
So what's the line for like the A?
Yeah, that's Isabel being fancy. Shoot, we haven't talked about the line yet.
Oh, that's probably IB.
We will talk about that. It means what this says is what it means. So it's a question that we want to ask often enough that we do have a symbol for it. So we'll mention what that means in a minute. The other thing to say is, like, intuitively, what does this mean? If someone walks up to me, like, let's look at C, for example, my first intuition is that, like, there's a 10% chance that they're IB, right? Because that's all I know in life. I don't know anything about them. But then I spy in their bag. I see that there's a pencil pouch. It's like Sherlock Holmes or something, right? And I'm like, I revise my estimate of whether they are or aren't an IB student. I'm going to revise it from 10% to 16%, right? Because now it's pretty clear that this person has a pencil pouch. And given that someone has a pencil pouch, the probability that their IB is a little more. It's actually 16%. I made up all these numbers. Who knows? But you know what I mean? Okay.
You went
So,
around and count them.
yeah, I should. I mean, from my experience, it is true that it's more likely that that's the case, right? But I don't know what the numbers bear out. So this is, you may have heard someone talk about this too. This is like called like Bayesian thinking, right? Like this approach to probability. Like we're revising our probability, and it's named after a famous mathematician named Bayes. So that's why it's called that. And conditional probability is like thought about all the time in life, right? I mean, and I said it's kind of in that Sherlock type situation where you're like trying to figure someone out, right? Would be a good example of when that comes up. Conditional probability is like a powerful thing. We're always like revising our probabilities in life as we encounter new information that like affects that probability. Thank you. Yeah, it's bigger than math class, Daniel. Okay, all right. So then let's talk about D. Are these independent? We didn't really talk too much about independence, but Amy, can you describe like what this says? You have a question mark here. It looks like you're asking yourself a question. Can you quantify what this means? Say it in English.
The test for independence is either probability of A given B equals probability of A, or probability of B given A equals probability of B, or probability of A times probability of B equals.
Okay, just describe the one and why it makes sense. Why does that make sense? I don't know what any of that meant, but talk to me about in English what that means.
If the probability of A given if the probability of A given B equals the probability of A, that means independent.
Why?
Because that means like one doesn't affect the probability of the other.
Okay, that's what I want to hear. That's what this says is that if someone's like, if I come up to someone and I'm like, 10% chance that you're IB, and then they pull out a pencil pouch and I'm like, still 10% chance, then that would mean that those two factors are independent, right? Like it doesn't matter if you're like, but I have keys in my pocket. I'm like, still 10% chance that you're IB, right? Like that maybe doesn't matter at all. Oh, but I have hair. Still 10% chance that you're IB. Like that's not, maybe those two factors are independent, right? But if you pull out a pencil pouch, maybe I'm like, oh wait, hold up. Not independent. Those two things matter. Those are two factors that affect each other in an important way. Okay, so we can check to see whether this is true, is what she's saying. Is it true that like, is the probability of A affected by introducing the new piece of information B? If not, then independent. But if so, then not independent. This is so let me actually check her numbers on this. So the probability of IB given pencil pouch, I like the IB PP, is 0.16 because we already computed it. And the question is that equal to just the probability of IB in general? And the answer is no, so let's move on, right? Okay. So that's like, you just learned everything about independence that we need to learn, but now we'll come out and say it all again, okay? You ready for me to say it all again? Prepare yourself for that experience. All right, so actually I'll return to that previous example, and maybe if we have some time at the end here. So I think it's really good to have that entire discussion we just had before showing you this formula, because in the end you understand this formula, this idea of the probability of B given that A has occurred. You understand this pretty intuitively just from the picture, don't you? Like, maybe you're thinking about like the football over the volleyball, aren't you? Do you like that analogy? Yeah. I picked the volleyball because that's the best sport. Okay. I will have a little bit of a caveat here. It's not always true that these areas are in those shapes. There's nothing special about the shapes. The general idea is still the same, though. Okay, so you can imagine more exotic situations where they're not those shapes. That's for sure. Yeah. Oh. All right, so what does this say again? Let's make sure we understand. This is, in English, this is B given A. B slash, or pipe. Sometimes it's on the keyboard, right? Above, what is it?
Above enter.
Above enter, it's also got a backslash on it. Okay, so, you're right. Anyway, it's a pipe. All right. And we read that out loud as B given that A has occurred, right? And we're in that situation a lot in life, that we know that something for sure has happened and we want to know. Anyway, so this is called conditional probability, and you might call A like the condition that has been imposed. Like, and again, it's kind of, you should picture this as like kind of restricting our sample space. Like I said, the tunnel vision look. This is our new world, A. So that's the denominator now. It's not the whole sample space. This is a nice applet. You can figure out what it means. Go click on it at home. But let's keep moving. Is that okay? Do you like that formula? All right, and then I'm about to put on this slide the 3 things that Amy just said, but you weren't paying attention, so we're gonna put it up here again. One way you could say that 2 events are independent then is by saying that this is true, which is exactly what she wrote on the board. Might even been exactly like that too. Is the probability of A affected by the probability of B? I like that way of thinking about it. If B occurs, does that leave the probability of A unchanged? Then they're independent. They don't affect each other, like in a literal way. They do not affect each other's outcome. Or, equivalently, the probability of B, you test to see if that's affected by A occurring. Or, equivalently, you could test their product and see whether that's the intersection. Like on the warm-up that you just did, the intersection was 0.08. If they're independent, then the product of the 2 probabilities of A and B, or whatever it was, IB and DB, should be the probability of their intersection. If that wasn't true, you can test it on the warm-up. That wouldn't have been the case. So that would be another great way to test for it. All of those things kind of like make sense intuitively, but also these are algebraically connected. Like if we just like take this and actually write what this means, this says what? The probability of A is equal to, the probability of A given B is the probability of A and B over the probability of B. Do you see how algebraically that's equivalent to the other statements? Can you do a rearrangement on this piece of algebra to get this statement? Maybe some of this, right? Some of that action. Okay, good. Okay, you see that? Do you think you can do a rearrangement to get this? That's okay. So algebraically, they all make sense that they're equivalent too, but also from an intuitive standpoint, that should make sense that they're all the same. Okay, so one way or another, you now know how to test for independence. Once we've introduced this too, once we've come out and said this, we realized that like when we said the multiplication rule a second ago, we said if 2 events are independent, then you can multiply and get their probabilities. We also just said that the, what's it called? What's the other direction called?
Right.
If this is true, then they're independent. That's called the, no one knows, it begins with the C.
Causality.
The converse? It's if and only if, right? If
Condition.
I said it's converse. Yeah, sorry. It's all good. If they're independent, you can multiply to get their probabilities. And if you can multiply to get the intersection. And the converse is true too. If this holds, then it must be the case that they're independent, okay? So both things are true. Let's talk about trees. I think this will be a helpful example to talk about the power of trees, okay? We have all these different tools and we're just like throwing them at you, okay? So stand by. We've got 2 identical cookie jars. Imagine that they're opaque and dark inside, okay? We're gonna basically just flip a coin and pick one. So, I don't know which, doesn't matter. They're not labeled A, I'm just like picking blindly from a cookie jar, one of the 2. One of them, jar A, has 3 chocolate chip cookie and 2 peanut butter. Jar B has 2 chocolate chip and 4 peanut butter. All right, so you can see the stakes are high. So how can we, maybe we right away we start drawing a tree just to picture the situation. Here are all the life options you have, okay? We could be in this world or we could be in this world. Okay? And the probability, I'll label each, excuse me, I'll label each branch with its probability, right? So I already told you, it's not really in the problem, but I already kind of told you they're exactly the same. So therefore we're just, and they're opaque and dark inside, and it's basically just like we're flipping a coin. We don't know which one is which. We're just going to reach in, and that has a 50% probability. Okay, so now I want you to actually tell me though, once we're inside these, cookie. You're inside jar A now. What's the probability you get a chocolate chip cookie, given that you're in jar A? Or what about a peanut butter cookie? What'd you say for those? First one is 3/5, and the second one is 2/5. Okay, and then do the same thing for jar B. What is that? Yeah, 1/3, 2/3. Is that what it is? Okay. And by the way, the probability, what would you say 3/5 is? We might say that 3/5 is the probability that you get a chocolate chip cookie, given that you're in jar A, right? So just so you know what that 3/5 represents. Okay, and then you could say something similar for the other ones. All right, so then I don't know how to answer the question yet. What's the probability of picking a chocolate chip cookie? But I do know how to answer like some easier questions. Like for example, what's the probability of both getting jar A and getting a chocolate chip cookie? I think I can figure that one out. It's 1/2 times 3/5. Right? We're just like going down this tree. Okay? So that comes out to something. And I could ask another question, like how about the probability over here of jar B given, and getting a chocolate chip cookie? What would that be? 1/2 times 1/3 equals 1/6. And those are actually the only situations I care about for this particular question, because that's the question. But just for fun, let's do the other ones, okay? So what is this? The probability of A and peanut butter cookie. So compute that, and also compute this. The probability of B and peanut butter cookie. So that's 1/2, 2/5. And this is 1/2, 2/3. All right, so what do we get there? 1/5 and 1/3? And if this is really representing every possible like world line that we could be traveling down, then what might be true about all these probabilities? Hopefully they add up to 1. We have like our own little probability distribution here. So quickly verify in your mind that these do in fact add up to 1. Go ahead. Furthermore, actually, you might be able to, maybe you're doing it like this in your head too. This is actually, we can actually divide it even further. What does this add up to? It should be that these add up to 1/2 and 1/2, right? Are you feeling that in your mind? Okay. Because it should add up to like what the branch was back here. Think about why that's true. Okay. So I think we have all the outcomes. They do add up to 1. Everyone's verified? Okay, good. All right, like I said, we didn't need to know about these other ones. The only ones I care about right now are these two. And then what do we do? When you think about unequally likely outcomes, what do? We have a distribution. We just, what's the answer to the question? What's the probability of picking a chocolate chip cookie? Add them up. Right, exactly. So 3/10 plus 1/6, and we'll call it a day once we figure out how to add those two fractions. Okay. 30ths I like. Let's see. Wait for it. 9 plus 5 is 14/3, 7/15 maybe? Check my arithmetic.
Yeah, that's right.
I feel like that's the answer to the question we wanted. 7/15. Do you agree? Do you like what we did? Do you have any questions about what we did? Do you see how a tree is useful in what we did?
Yes.
Again, a Venn diagram, same thing. Like a Venn diagram, as soon as you make it, like, might be a little tricky to set up, but then lots of questions become very easy once you have that picture in front of you. And the same is true for a tree. It's a pretty powerful tool. We can draw a tree. It kind of clarifies our thinking in a nice way. So, okay, good. And then let's not lose this example. Let's continue and ask this question with that same example. Assuming you picked a chocolate chip cookie, what's the probability it came from jar A? That is, I see you walking out of the kitchen with a chocolate chip cookie. What's the probability that you had your hand in jar A a second ago? Right? This is the question. Is that clear? It's like a completely good English sentence. Now how do we think about that in terms of math? The math we've been talking about. What are we looking for? The probability of what? Can you give me some symbols here?
Probability of
A given. Yeah, the probability of A given chocolate chip cookie, right? By the way, that's kind of a flip of the probability. I know the probability of a chocolate chip cookie given jar A. 3/5, I think, right? I'm just going back and trying to remember. Right? That's
Yes.
but that's a different question. We're doing a flip of the condition here, right? Okay. So I'm just like gonna obey my formula that we talked about earlier. Again, it should kind of make sense. We're restricting down the denominator. We're kind of like, this is our world now, chocolate chip cookie world. And up in the numerator, we're looking for that intersection, right? So that should make sense intuitively too, but it is also just the formula. That's fine. And hopefully we have these things. The chocolate chip cookie, the thing in the denominator, we just computed it, 7/15. That's the overall probability without restriction of a chocolate chip cookie. And the probability of A intersect chocolate chip cookie is, I don't know, I didn't remember it. It's 3/10, right? Because we said so. Okay. And that equals something, I don't know. This is the hard part. 45/70. Let me write that down before I think harder. 9/14. I'll take your word for it. 9/14. Yeah. 5 into 70 is 14. Okay. Are we feeling good about that? Okay. Lots one can do with these questions. All right, and then I'd also like to just, I think this would be a good use of time. I'd like to go back and do one more Venn diagram problem. I think this is a good one to do, so let's do it. And if we have time, we'll do some more other things too. So yeah, we'll start by making a Venn diagram and all that same stuff. And I'll just run this as I don't anticipate any huge surprises here, so I'm just going to call some people up in a minute. I'll give you a chance to get started on this. I'll call people up in a minute to do these for us. I just want to make sure it's really clear that this is not about like a particular restaurant, okay? Is that clear? Yeah. We're not talking about like any particular restaurant. Okay. We like to just kind of make fun of our book because, did you read any of the book problems last night? There was a problem about M&M's. Oh wait, did I say that out loud? No, it was about a popular candy, thin coated candy colored chocolate with a W on it. No, I don't know. It's so funny how out of the way they went to like avoid the word M&M. It was just kind of funny. So
But
I don't
they
know,
also
maybe they have to, like,
didn't
pay
use
it.
M&M colors though. It was like yellow, orange,
Oh.
tan, brown.
well, they used to have
It was like they used the retirement home colors. They love beige.
Do the problem about prostitutes. Yeah. Yeah, there are lots of ways to write not. You can write you can write this way, or this way, or this way. Huh? Oh, that's a good question. How to write all those? Maybe we don't care yet. But let's ask that though too. I think that's a good question. Okay, so let me get some people up here to do some of these then. All right, Sydney's gonna. You're gonna just do the diagram, and it's not one of these. Can you just give me the areas on that? When you come up and do it in a minute here. We'll give everyone a chance to think here. Give me 1 second. This will be Stephen H. Oh wait, she already did one. All right, whenever you're ready, people, other people can come up here too. Are you not Stephen H? Yeah, that's you. I think it looked like an M probably. I can't read. No, it looks, it's definitely an M.
I have problems with
Anyone else need the 5 days sign up sheet? I'll send it around tomorrow. Kate, where are you? You can come up and give your notes. All right, let's just check the first couple. Maddie and Kate are coming up soon here. First of all, am I right that like once Cindy draws that picture and like we have those areas labeled, that all of these questions, like almost all of them, like just fall right out, right? Like once you've done the picture, like she's already done the work of some of these, and if you were just to ask this question, it might be like a little hard to conceptualize. Like the picture turns something that's like kind of a hard thing to get our mind around, a difficult problem, into like a trivial problem. So we really like pictures. Point 4, do you agree with these answers, A, B, and C?
This is really hard for me to do.
So a burger, but does not order a Frosty. How would you, is anyone willing to tell me, did you come up with a way of writing that? Haley asked. How would you write that, maybe? Probably a burger, but not a Frosty. Is there a good way to write that using like our set notation stuff? Thomas, go ahead.
A and B complements.
Okay, and what do we have? F, B. I'm using F and B.
B and
F. Or yeah, okay, so
F complement and B.
B and
Oh, that's why I said B in the last one.
not F?
Yes.
Okay.
Big word. Oh.
Yeah. He speaks Spanish. What is this one? It'd probably be F and not B, right? Some of these get a little interesting though. Can you write this down?
Wait, so the last one says that they're dependent?
They are dependent, like apparently.
Should I just pass it?
Yes, they're dependent. Yeah.
Like, is there a lot of